Okay, next talk. Whitham Reeve, survivor of an 8.5 earthquake up in Alaska. I guess they didn't even see a ripple in the water, but that's a different story. Whit is a space weather enthusiast who's been a SARA member since 2008. He currently is contributing editor of the SARA Journal and previously served SARA as the journal editor and as a member of the board of directors. And I'll tell you what, people, if it wasn't for Whit's input to that journal, it would not be as fantastic as it's been. He's really one of the prime content providers for that journal. So I really appreciate him, and especially when we go round and round about formatting and things like that. He's really good. So, okay, Whit, go ahead.
Okay, thanks, Rich. Can you hear me okay?
Yes, you're good.
Okay, good. We're going to talk about HF Meteor Trail reflections observed at Anchorage, Alaska in USA. And I always say USA because there's an awful lot of people that think Alaska is part of Canada, and it's not. So here's what I'm going to talk about for the next 45 minutes, and hopefully I'll get through this whole thing. Who I am, what I do, meteor fun facts, the concepts behind meteor trail reflections, considerations for observations at HF, high frequencies, instrumentation, observations, conclusions. So that's the contents. Who I am, been a SARA member since 2008. Been a contributing editor to the SARA Journal for a while now. I don't really know how many years. I'm going to guess maybe 4 or 5, maybe even more than that. I'm from Alaska, lived here, educated here, worked here all my life, and was in telecommunications and radio engineering. Ran my own engineering company up until 2009 when I retired the firm. And now I occasionally manufacture instrumentation for radio astronomy applications. I do some consulting work for the University of Alaska Geophysical Institute at the HARP facility up near Gakona. And one of the things that I've done over the last maybe 10, 12 years is building 3 observatories in Alaska. And here's a map of them. Let me put up a spotlight here. Hopefully that's going to work. No, that's not working. How about a laser? Yeah. Can you see my mouse or the laser? Okay, good. Here's where I lived in South Central Alaska, and I first built this observatory here in 2008, and it's so noisy here, so electrically noisy, that I built another one down at on the Kenai Peninsula, southwest of Anchorage, and it's much quieter down there. It's a rural area. I can drive to it. Takes about 3.5 hours. And then I was invited to do something up at the HARP facility up in Gakona, and that's a little bit in the interior of Alaska, almost a 4-hour drive up there and through the mountains. And these, the HARP and the COHO are remotely controlled. I use primarily TeamViewer for that. COHO is not attended at all, except when I'm down there. And I just came back from there last night. HARP, there's staff that works at the facility that really has really helped me out up there. In fact, without them, I don't think I could have done it, built anything at HARP. Okay, so I'm not having any luck advancing my slides. I don't know why.
I still see your laser pointer on. Maybe if you turn that off.
Yeah, let me try to, that's a good idea. Let's see, just go back to a mouse. No, I didn't do anything. I'm going to stop share and then I'll come back to it. I don't know what the heck is going on. Oh, there we go. Observations vary with the observatory. I mostly do things having to do with the sun, space weather related things. Also do Jupiter radio, primarily at HARP, because it's a nice quiet site for that. I'm interested in radio science and radio propagation, solar flare effects on propagation, meteor trail reflections at HF, which is what I'm talking about today, and then geomagnetic using the SAM-3 magnetometer, which is used in the Space Weather Underground program. So that's kind of a nice little project for me. Let's look at some meteor fun facts. Well, not facts maybe, well, let's call them estimates. There's a lot of information that indicates there's trillions of tiny meteors that enter the atmosphere each day. These are dust grains that are left behind by asteroids and comets. They have a very small mass, 1/10,000,000th of a gram to maybe 1/10 of a gram. Their diameter varies from 2 micrometers to maybe 2 millimeters. And the thought is that there's equal mass distribution of each particle size. So there would be 10 times more that are 1/100th of a gram than there are 1/10 of a gram. Their speed ranges from about 11 to 72 kilometers per second. And that's determined by the gravitational force of Earth and the sun. And there's an estimate of about 100 to 1,000 tons enter Earth's atmosphere each day. Now, I have no idea how that number come about. I have a feeling that it's a swag, swinging wild guess. And there's another estimate that there's 5,000 tons of this debris reaches the Earth surface each year. So those are kind of fun facts, fun estimates. And I'm just going to spend a little bit of time on concepts. But when a meteor enters the atmosphere, it collides with atoms and molecules that make up the atmosphere. And the kinetic energy of the dust grain is converted to heat, which vaporizes the surface atoms. And this is called ablation. And these ablated atoms are ionized. And they leave a long, thin trail of ions and free electrons. And the number that I've read is these trails are about 50 kilometers long, has a paraboloid shape, and they primarily are in the 85 to 105 kilometer altitude range. And it has pretty much been determined that the minimum altitude that these reach is in the 80 to 85 kilometers. So you're not going to see radio reflections below those altitudes. Now, the positive ions are pretty high mass and they don't interact with radio waves, but the lighter free electrons that have been released from the dust grain as it burns up, they do readily react at radio frequencies. And the electron densities in the trail are far higher than the surrounding ionosphere. And these are given in electrons per meter. Usually your electron density is given in electrons per cubic meter or maybe electrons per cubic centimeter. But when we're talking about meteor trail reflections, we're talking about electrons per meter of length of trail. And that could be 10 to the 10th to 10 to the 16th is the number that I've seen. Now the radio waves easily react with the higher density trail. And by interact, I mean they are reflected or scattered. And meteor trails have been broken down into two types of densities, an underdense and overdense. And there's a number of electrons, 10 to the 14th electrons per meter, that is kind of the agreed upon separation between underdense and overdense trails. And when we're talking under or overdense, we're talking about the electron density. So you can say this is kind of an arbitrary number, but that's what's been agreed upon. And the underdense trails are far more common by roughly a 20-to-1 ratio. And that's been my experience too in the observations that I'll show you later. Now, when a radio wave sees or interacts with the meteor trail, the underdense trails are, the radio wave is scattered coherently. And that means that the radio wave interacts with the electron re-radiates, and all of these electrons more or less are working in concert, and so they scatter coherently. Overdense is much higher density, and the radio waves probably do not penetrate very far into the trail, and that's so they are actually reflected rather than scattered. So those are kind of the two basic concepts. And the meteor trail reflection, and I'm going to call these echoes also, you have a transmitter that's sending out a radio wave, and it is echoed or reflected off the meteor trail, and it's the incident angle and the reflected angle are equal, and then that's what you receive. Now this two-dimensional drawing here makes it appear that this is a vertical plane that connects the transmitter propagation path with the receive propagation path, but chances are it's tilted to some degree. And so it's really a three-dimensional problem that we're looking at here. And there's some trigonometry involved in determining all this. And I haven't really monkeyed with that too much, but because I'm more interested in what I see and not how it gets here. Now, the concept is that this is a bistatic radar. The transmitter and receiver are at fixed locations, but they're separated by some distance. And I use the transmitters, the WWV transmitter station that's near Fort Collins, Colorado, and the WWVH that's on the island of Kauai in Hawaii. And both of those are in a neighborhood of about 4,000 kilometers away. So those radio waves that are emitted by these two stations have a long ways to go before they get to Anchorage or in my vicinity. WWV is almost true east of Anchorage. WWVH is almost true south of Anchorage. So this shows the paths that are being followed here. So we have the WWV transmitter over here on the right-hand side and a 3,800 kilometer path to Anchorage. WWVH is down here on the lower left, and we have about a 4,400 kilometer path up to Anchorage. And I presume that this would very roughly define the reflection area, so that there are, what I mean by that is that there are meteors in overhead here, and the reflections are coming, the radio waves are being reflected in this area here. And it's just total speculation on my part. I have no real idea about where those meteors are that are causing the reflections that I see. Now, when you're observing meteor trail reflections at HF, especially in my case, you have a special problem because those radio waves have got to travel very long distance before they even get to Anchorage, or even in the vicinity of Anchorage. So this means that we have multi-hop or multi-mode propagation paths. And I thought about this for a long time, and finally I thought to myself, well, maybe these reflection points, either in the ionosphere or on the Earth's surface, maybe those are, I could view those as virtual transmitters. And the meteor trail reflections that I see at my receiver here on the far right are because of these reflected radio waves that are coming down off the ionosphere, or maybe going up from the Earth's surface toward the ionosphere. And so in other words, the propagation geometry must be suitable for those radio waves to get into my vicinity before they're even going to be reflected off the meteor trails. So a path must be present to the transmitter and from the transmitter to the receiver before this will even work. And I found this to be true. In other words, when I'm seeing these reflections, I'm also seeing the direct path or an ionospheric path to my receiver from the transmitters. Now, the propagation can use the F or E regions or a combination. They're using even a concept of an HF waveguide between the F and E layers that may be involved here. I'm not real sure. I haven't been studying this long enough to really figure out just exactly where these reflection points are that are causing the meteor trail reflections. But there are certainly, because of the distances involved, there are a number of hops or modes involved here. The height of the ionosphere definitely changes from day to night throughout the day. And the angles that are involved here for a 1 or 2 hop, which would be probably pretty rare, we're talking 15 degrees angle between, that would be the angle between the Earth's surface and the radio wave being reflected. A 4 hop would involve a 34-degree angle. So we're looking up at the sky. We're not looking at the horizon for these. At least that's what I think. Now, another thing that comes into play here is that there are daily, seasonal, yearly, and long-term variations. The daily variations depend on Earth's rotation. As it's moving around the sun, you'll have one side at sunrise that's pointed toward the path of Earth's movement in orbit. And so it's going to basically sweep up meteors on that. But when my station rotates around to the nighttime, then the meteors that are coming in have to overtake Earth to get there. So when I see the meteor trail reflections, I see them in the morning in this area here. Also in the seasonal variations, you've got the Earth's tilt in its orbit as it moves around the sun. And so for me, September would be a better time than say March. You got long-term variations that are related to the sunspot cycle, and that determines the sunspot cycle is going to determine the propagation conditions. And like I said a few minutes ago, I have to have propagation to Anchorage before I'll see meteor trail reflections. And I'm noticing that this year. Last year was and last winter, I saw lots of Meteor Trail stuff. So far this year, I haven't seen that much. And it's I think the sunspot cycle has something to do with that. How about the instrumentation? Well, it's actually pretty easy to set up a system to do this. In my case, I have an 8-element log periodic antenna that has a design range of 18 to 32 megahertz. And I run that through a multi-coupler, and then I run multiple receivers off of that. And I use mostly the R8600, the ICOM wideband receiver, or the R75 general coverage receiver for that. And then I take the audio frequency outputs from these receiver, run them through a audio mixer, and that allows me to control what's being recorded through the sound card on my PC. And then of course, to make all this stuff work, you need a rotor controller and power supplies, and I use NTP time servers to control the timing on my PCs. So there's a lot more involved than just a receiver and an antenna, but it still doesn't have to be that complicated. That's a picture of that log periodic antenna. It's right outside my my window here, and it's about 13 millimeters above ground level. It's horizontal and rotor controlled. And typically I have it pointed west, or I'm sorry, I have it pointed east toward WWV, but I have pretty good reception from WWVH south of here in Hawaii too, with it in that direction. So those are the receivers that I primarily use. I'm looking to build dedicated receivers that would be fixed tuned individual cheap receivers, one for each of WWV, WWVH frequencies, and that'll free up my more expensive receivers for other projects. For me, this is a long-term project, and I just let the system go and record 24/7, and then I come back every so often and look at the data and process the data. I use a small form factor PCs that have a real line-in audio port and real RS-232 serial ports. And this hardware is, for me, has proven extremely reliable. Of course, I'm running Windows 10 Pro, which is not that reliable. But it seems to be controllable, and I've slowly figured out how to control Windows 10 inevitable updates. The software I use primarily is Argo, and the Argo was originally designed for very low speed digital modes, HF digital modes, but it's turned out to be pretty doggone good for Meteor Trail reflections. I know other people use this, and it's worked out well for me. And what Argo is doing is when you feed the audio in to your sound card, that's demodulated audio. And I run in upper sideband or lower sideband mode, and then I detune the receiver so that I have a nominal 1000 hertz tone. So what you're actually seeing with Argo is the demodulated audio. And you can see on this chart here that I have it centered about 1000 hertz, plus or minus 20. And so the meteor trails then show up, or the reflections show up in that. It's kind of like a horizontal spectrum waterfall. Now, every once in a while, I see these spurious signals drift through the band that's being displayed on the waterfall. but they're very easy to discriminate or differentiate from what I'm from the meteor trail reflections. You can see some meteor trail reflections in this image here, these blips and these streaks down here. Okay, I'd like to spend a little bit of time on my observations, and I'll give you a verbal description of them first. The audio that I hear are 1 second or less bursts of tone. So in other words, that demodulated 1000 hertz audio, I'll hear bursts of tone or maybe tone enhancements, increases in volume. A stream of meteor trail reflections sounds like low-speed CW, demodulated to 1000 hertz. And the short tone bursts or the short duration meteor trail reflections are usually Doppler frequency shifted, and they'll have a bell or a multiple bell sound, or even sound like a wind chime. So it's actually kind of musical and really interesting to listen to. The problem is that I don't have any actual audio recordings of it. So otherwise I'd really like to be able to play it back to you. It seems like I get too mesmerized by the sound to actually hit the audio record button. Now, as far as detection times and rates, for me, most of my detections are between 4 o'clock and 9 o'clock in the morning. Now, I'm not up at 4 o'clock in the morning to listen to this, but Argo is. Argo's running 24/7, and so I'm getting images of all the activity. And then when I get up, I can listen to it from, say, 7 to 9 o'clock or something like that. So it's generally before sunrise at Anchorage that I'm detecting these meteor trail reflections. Sometimes I'll have a detection that's outside of the morning time frame, but I'm not real sure. Those may be anomalous and not actual meteor reflections at all. And for meteor reflection events, I recognize them during all months, but not every day. So in other words, when I go through my images, my Argo images, I'll usually find some activity in every month of the year, but a lot of days there's nothing going on. And that has to do more with propagation than anything, I would think. June 2020 produced few records, while January and October produced many records. So, the rate of detection is probably more dependent on propagation than the actual number of meteors that are coming down and causing a reflection. And I noticed that the number of echoes decreased as propagation improves with the morning ionosphere development. So in other words, as propagation from these stations far, far away improves, the number of echoes that I see decreases. And so the favorable window for me is about 3 hours in the morning. Now, when these reflections are coming in, I don't know if they're coming from WWV in Colorado or WWVH in Hawaii. The audio is not recognizable. I can't hear the woman's voice for WWVH or the man's voice for WWV. So I don't really know where what the source is. But I've been getting really good results on 15 megahertz for the most part. I do have one image I'll show you in a minute that is for 25 megahertz. And the echoes generally, according to the Argo software, the echoes are generally 10 to 20 dB above the background. Doppler frequency shift that I see is plus or minus 5 to plus or minus 10 hertz. There are some exceptions where they're plus or minus 20 hertz. Now, plus or minus 20 hertz is the limit of my Argo waterfall. So if there was Doppler shifts that are greater than that, I wouldn't see them in the images that I'd get later. Now, the one thing you'll notice here is that the Doppler shifts often favor one polarity over the other. In other words, most of the echoes that I see may be a minus from 0 to a minus 5 hertz. Many more of those than say 0 to plus 5 hertz. And I'm not real sure about why that is. It possibly could have something to do maybe with the Meteor radiant or its direction with respect to the transmitters or the receiver. So I'll show you some of those images in a minute that show that favoritism. The short duration echoes appear as ticks or blips. And this is more than an hour-and-a-half stream of short duration echoes. All these little blips here that you see are short duration echoes. And you can also see the, and I'm going to call this the direct path in the middle here. It's not a direct path, it's a multi-mode propagation path, but it's what I'm actually receiving from the station and not being reflected by the meteors. Now these short duration echoes last only for a fraction to a few seconds. Argo software cannot resolve fractions of a second or even a few seconds. So I don't know exactly how long they are lasting, but the streams can last up to 2 hours, and they just come in continuously for 2 hours and then taper off. There are also long duration echoes, and these probably correspond to the overdense trails. They all have horizontal features or stripes as shown here. And you can see where this has been split into several different streaks here. And these all last longer than a fraction of a minute. Some last as long as 5, maybe 7 minutes. This particular one that I'm showing here is a 7-minute echo. And they start quite abruptly and then trail out. And most of the long duration echoes that I see are striated. In other words, they have separate features here that are horizontal lines that make up the long duration echo. Now, I don't know the true cause of this. It could be interference between reflected radio waves from different parts of the trail. It could be meteor fragmentation, and I'm seeing reflections from each of the fragments. It could be a meteor group that is causing the reflections, or it could be high altitude wind shear. So there's a lot of things that could be causing the striations, and I don't really know yet how to figure out what is causing the ones that I see. Okay, here's some observations, and I have the text description down here below of this image, and you can see here's what I call the direct path that crosses the middle at exactly 1,000 hertz. And then we see the meteor, we see some blips here, which are short duration meteor trails, reflections, and then we see these striated features here. And those are the long duration trails. Here's a composite of two 12-minute Argo images. So this is a total of about 24 minutes. And you can see all kinds of short duration things going on. And we also have a nice long duration arrow that's kind of got a bulb type beginning here before it gets striated. This is a single 12-minute Argo image, and you can see there's a long duration echo here that's been striated. 1, 2, 3, 4, 5 striations to it. Here are some others over here. Another, it looks like maybe another one here. And notice that the Doppler shift is on these are less than 5 hertz. Here's some more long duration and short duration. This is 2 spliced images. So this is from 1757 to 1812 UTC last January, or January of 2020 at 15 megahertz. And you can see that the long duration echoes are striated here. This one seems to be a single trail reflection here. This is six spliced images. And so what I did is I took 6 Argo images in a line, spliced them together, and you can see some spurious signals drifting through here. They look like they're almost vertical lines. And what I did to accentuate the Meteor trail echoes, most of them being short duration in this one, is I've stretched the image vertically. So I left the length fixed and then stretched it vertically to kind of amplify the effect of the short duration echoes. And if you look at this, you'll notice that most of the activity seems to be on the positive Doppler shift side versus the negative Doppler shift side. And sometimes that will be switched around. It'll be more negative than positive. So this one here shows primarily a positive Doppler shift. Here's a nice long duration echo. I think I showed this earlier in a smaller scale, but this one lasted about 7 minutes at 15 megahertz. And you can see the striations here, the abrupt beginning. Sometimes this is curved. The beginning is curved. Here's a dual frequency record. So here I've shifted. This would be one frequency down here at 990 and another frequency at 1000. This line that you see right here is spurious. That's not a received signal. So the frequencies that I was looking at here are 15, 20, and 25. 25 would have been at 1015 demodulated frequency. So at 15 megahertz, I saw the reflection, but not at 20. I'm sorry, did I get that wrong? Yes, I did. This is 25 megahertz at the bottom. So the reflection occurred at 25 megahertz. And that was the only day that I saw anything at 25 megahertz. So let's look at some conclusions. Yes, you can receive Meteor trail reflections at Anchorage, Alaska, using time frequency stations that are 4,000 kilometers away. The demodulated audio consists of short tone bursts or enhancements with a bell sound or a sound like a wind chime. Long duration bursts have a wavering tone. If the Doppler frequency shift is more than a few hertz. I don't think the human ear can detect anything less than 5 hertz. So if the Doppler shift of the echo is more than that, then it's a wavering tone. It's kind of a weird sound. I see Doppler shifts up to 10 hertz. There are some exceptional outside that range, but mostly they're confined within plus or minus 10 hertz. And when I have large numbers of short duration echoes, they generally favor one frequency shift polarity. In other words, they may be mostly positive or mostly negative Doppler shifted. And the echoes are pretty strong, usually 10 to 20 dB over the background noise level as measured by Argo. Now, I don't know if that's a true signal to noise ratio, I doubt it, but that's what the Argo software indicates, that they're pretty strong. I see them mostly in the early morning hours, and that makes sense, looking at the geometry of the situation. Echo streams last up to 2 hours, and individual long duration echoes last up to 7 minutes. At least that's my observations. So that looks like I ran out of time and ran out of slides all at the same time there. Here's some references that you might want to look at. All of the technical data that I showed at the very beginning, the fun facts, they came from these 4 references down here. Now, the McKinley Meteor Science and Engineering book is considered kind of the Bible of meteor science, and it's really comprehensive. But I also found a lot of value in these other 3, the Goodman Meteor Burst Communications, the Shanker Meteor Burst Communications, and Sugar's paper on radio propagation by reflection from meteor trails. Those are really valuable resources. In fact, in many ways, I think they're better than McKinley, because the focus of these other 3 are radio, whereas McKinley talks about the entire field of meteor science. So there's a lot of stuff that you have to filter through to get to something usable in the radio arena. So that's pretty much what I've got going today. And if you have any questions, I'll try to answer those. And what I'm going to do is I'm going to stop sharing and then look at the chat.
Well, you got a number of questions and multiples from a couple people. So I'm just going to go down and start with Lester. Can you sum up a couple of your questions into one question?
Yeah, except of course, well, it's not just a question, but a commentary. The first thing is, I got all those nice receivers, but for less than $200, you can get this little box that receives all of HF and generates multiple receivers. When you look at it on an IP stream coming out, you'll find them called Kiwi or Fly Dog. And I forget, I think it was originally an English thing, but now replicas are coming out of China with no difficulty. I've got one sitting here. There's a whole network of them around the world, as a matter of fact. If you wanted to watch WWV at various locations in the world, you could bring those up and listen to them just as you're doing right now.
Right. Yeah, I'm aware of those. And but for my purposes, I'm pretty satisfied with the setup that I've got. Having receivers, the audio output from the receivers going into Argo and recording Argo. I've got about 300,000 Argo images now. So there's a lot of data in there that I don't think I could have gotten any other way. But
you can feed these receivers into Argo just as you do right now.
Yes, I know.
Okay. Doug Manchester, could the spurious linear signal be a passing satellite reflection?
Yes, they could be. But most of the spurious signals that I see are not nice linear slanted lines. They may change direction. They may have some curvature to them. So I think that they're probably locally generated. In other words, they're self-generated RFI. But yeah, I definitely do see ionosons and over the horizon radar drifting through the passband.
And Doug also asked, he said he notices striations start wide and get narrower, something decaying.
Yeah, I assume that's what's happening, but not real sure about that.
Okay. William's iPad. William, why don't you come online, since I don't recognize your last name, iPad.
Okay, this is Bill Lyles.
Oh, hi. You go ahead and ask your questions to Whit.
I was just saying that I thought the slant lines were probably an ionosound. But I thought his presentation was very well done. And so are your receivers clocks GPS disciplined?
No, the receiver oscillators are not, but the PC timestamps are.
Okay, so some of what you see as Doppler may be in fact because of the receiver's oscillators.
Yeah, they could be, but when I have strong signals coming in, those lines are perfectly horizontal. Both those receivers are really stable. They are not referenced, but they are very stable. So I don't think any of what I was seeing was receiver drift.
Okay.
Okay.